Okay, off we go. Thanks for coming. Let's see here. Wow, this is actually not bad for the last day of the class on the Monday before Thanksgiving. So good for you all for coming. Don't forget to do the attendance quiz and the attendance codes right here, of course. Wouldn't it be a crying shame to forget to do this one, right? After staying for several extra days. Okay, so jumping back in, here's where we were last time. We just barely scratched the surface in preparation for working up Stokes' theorem. We talked about boundary orientations, and in particular, keep in mind that the word boundary, loaded word at this point, boundary means oriented. It means oriented according to a certain convention, and this is the convention. I don't want to go through the whole thing again, but the short version is that you put your thumb in the direction of the surface orientation. That defines a swirl by way of the direction that your fingers kind of start to wrap around your thumb, and how that swirl sideswipes up against the boundary is the correct, what we call induced orientation on the boundary. Okay. All right. So what do we do with that? So begins an argument that we've done several times before. I mean, at least structurally, this argument, different geometric circumstance, of course. But here we go. The claim is that boundary circulation is an accumulating quantity. Boundary circulation accumulates over surfaces. So, so what that means is if you have a big surface like this and you look at the boundary circulation, right, like so. Well, if you, on the one hand, were to look at the boundary circulation just on the left, and then if you were to look at just on the right, now notice I'm following the rule concerning orientation. So, loosely speaking, as seen from above with these normal vectors pointing up, counterclockwise, right? But again, very important to keep in mind it's much safer to use the right hand argument because clockwise, counterclockwise is perspective dependent per this example of how my finger is moving right here. Okay, so as usual, we see that it all cancels except for these two in the middle, and these two in the middle have opposite orientations, and so they cancel, and so we win. This is really very, very similar to the analogous picture that we draw in 6.2 in developing Green's theorem. It's really very much the same kind of theorem. And the pattern continues. Once you realize you have an accumulating quantity, then we can view that accumulating quantity as being a kind of a stuff. Once you have the idea that you're going to view it as a stuff, you can talk about how much of that stuff, circulation in this case, how much of that stuff there is per unit area. Right? If it's a substance distributed over the surface, how much of that substance is there per unit area? And we can compute this. And wouldn't it be nice if we had time to do so? But I'm just going to claim that this is the answer. This is what I'm going to call circulation density. It's curl dot in. So the unit normal vector matters. So this vector right here, how that piece of surface with its normal vector, how that piece of surface sits in space makes a difference. So that's why dot the normal vector appears in the equation there. Okay. All right, and then it's all over but the shouting, and we put all the pieces together in pretty much the same way that we have several other times. First, we start with the idea that we can think of boundary circulation as a quantity defined on surfaces. Now, again, this is a little counterintuitive. It's tempting to say, this is a line integral. Line integrals are computed on curves. And that's true. But I want us to think of this as you give me a surface. I'm going to define a quantity on this surface. And the quantity is given the surface, look at the boundary curve and compute this boundary circulation on that boundary curve. So you give me a surface, I give you a quantity. That's what we mean by a quantity on surfaces. And we argued that it is an accumulating quantity, wholes the sum of the parts. And then we further argued that any little piece of boundary circulation is density times size, and bam, we have ourselves a new theorem. Boundary circulation can be computed with that integral. And just copying, kind of ripping off from old arguments we've made in the past. Now you'll notice this little rewrite. I think this is a nice way to rewrite it. After all, this top integral here kind of looks like a scalar surface integral. It's got a scalar differential, or so it seems, right? But once you rewrite, once you recognize that the n and the ds together we can rewrite as ds vector, then this really kind of makes more sense as a vector surface integral, vector differential, vector integrand, dot product. Really makes more sense. So this is what I'm going to call our Stokes' curl theorem right there. How we doing? Is everybody okay? Everybody playing along? Okay, regularity issues matter. We do need it to be nice everywhere, C1 everywhere. No singularities, not so much as a single point being a problem. It's a very delicate theorem, as are all of these theorems. Okay, let's do one. Oh, I always get ahead of myself. Before we do one, let's flash back to this diagram. We now have this entire diagram filled out, frankly. So for a while, the missing piece was that right there. Well, now we know what a flux integral is. We've known that for a week or so by now. And we talked about Gauss's divergence theorem last time, I suppose it was. And now, Stokes' curl theorem says if you take the curl of a vector field and the boundary curve of a surface, then the line integral of the original vector field on that boundary curve, the flux of the curl through the original surface, which easier to write as just, like so, those will always be the same. So you recognize it's the exact same pattern. It's weird how this pattern keeps showing up. I've mentioned this before, but let me say it again. It's not a coincidence. The reason that this pattern for Stokes' theorem and this pattern for the divergence theorem and it's the same pattern for all of these theorems. The reason that they're all the same pattern is because they are in fact all the same theorem. They're all the same theorem. Special cases applied to different geometric circumstances. But that general theorem is let's see how to say this, too much for us to talk about in this course, but ultimately this is where this diagram comes from, right? I rigged up this diagram so that this would all work out by the same pattern, because again, that's how the general theorem works. Okay, and we're going to come back and do some more stuff with this diagram later on. Okay, let's see an example. Here we go. Compute the line integral. Vector field given, curve given. Notice, as we've seen in several other previous circumstances, this question does not announce itself. This question does not say, use Stokes' curl theorem. It just says compute the line integral. You got to figure out how to compute the line integral. Excuse me. Let's see here. How might we compute the line integral? We got a parameterization. We could pull back through the parameterization, a la early chapter 6. Right? That would be a way to go. Let me point out as well, if you want to compute a line integral, hey, maybe the fundamental theorem of line integrals. I mean, that seems like it'd be a reasonable candidate, right? So that's another thing we could entertain. And maybe that might work. Side note, Doesn't work, as it turns out in this case. And I'll come back after we finish the example and tell you why. We're going to use option number 3, this other theorem on the other side here. Again, we have these 2 theorems that both involve line integrals, and it's going to turn out that Stokes' curl theorem will work perfectly for us. So here we go. Going back up to the statement of the theorem, notice Stokes' curl theorem will compute line integrals by way of a flux of the curl. Notice further, though, only for boundaries. And this is a very important asterisk. Stokes' curl theorem does not just compute whatever line integral you want. It has to be a boundary. This is extremely important. If you have a line integral on a curve that is not a boundary, and if you write down, hey, flux of curl, and then go from there, maybe something like that, it's nonsense. It's absolute nonsense. So let me show you why. If your curve is not a boundary, then it's not a boundary of a surface, which means that there is no surface over which to even talk about a corresponding flux integral. So this is a big problem, right? This is not a condition, some little subtle condition that you have to check to make the mathematicians happy. No, this is a big deal. The line integral, it's not that the line integral doesn't equal the flux integral. It's that there is no flux integral. There is no domain on which to even talk about a flux integral. So this cannot be overemphasized. Do make sure that your curve is a boundary before you start tossing around ideas about Stokes' curl theorem. So is our curve a boundary? Well, here we go. Our curve was given parametrized like so. Make sure you can persuade yourself this is what that curve looks like. That's a kind of a chapter 1 flashback. So make sure you're good with that. If you have any problems with that, as always, come talk to me. Happy to help. But do make sure that you're strong, comfortable with being able to take this parameterization and produce this picture. And now, is this a boundary? And yeah, it is. Now, tempting, a lot of people would say no. A lot of people would say, well, yeah, but it's going clockwise, and boundaries are supposed to be counterclockwise. So first of all, this is not just going clockwise. And again, this situation, right? Is my finger going clockwise or counterclockwise? Well, it depends on your point of view. Right? So, as seen from below, this is counterclockwise. Secondly, this idea that boundaries have to be clockwise, that's not the rule. Right? The rule is with the right hand and the thumb in the direction of the surface orientation and the fingers and the swirl and the side swipe and all that business. Right? So this works just fine if you set up your surface to be the obvious disk oriented downward. And again, right hand, thumb in the direction of that surface normal. Look at the fingers of my right hand, right? And indeed, they swirl the correct direction. How we doing? Everybody okay with that? All right. Okay, so it's kind of all over with the shouting at this point. Our curve, wrong color. We notice that our curve is a boundary. It's the boundary of this region oriented like so, for which we write down the divergence theorem. We don't have to play orientation games and say minus, and the opposite orientation. We just correctly note what the surface orientation is. The surface orientation is upside down. It's downward instead of upward. That accounts for the seeming problem with the curve's orientation. And at this point, it's just a matter of plug and chug. Y'all can compute the curl. By the way, make sure that you can do this. Make sure you can take this vector field, compute the curl. You get that right there. So this is a formula we talked about back in chapter 3. Again, make sure you're proficient with not only that you remember the formula, but that you can crank it out comfortably, proficiently, accurately, reliably. Let's see, we already talked about the normal vector being downward, and this then turns into a super easy integral constant over a well-known shape. Problem solved. Questions? Everybody good? All right. Okay. Let's go back up here for just a quick second. Remember, our density is curl dot in. If you want to know stuff, it's density times size. So it's density in that sense. So this is what we would call a scalar density because we have a scalar quantity and a scalar size. Reasonable question to ask then, okay, well, yeah, but what does that mean about curl itself? Right, so curl.n, we've talked about what that is. Curl.n is density. It's circulation per unit area. But curl itself, how do we think about this? So let me remind you, we have been in an analogous situation before. When we were talking about the fundamental theorem of line integrals. When we were talking about the fundamental theorem of line integrals, we wrote this down first. We had our density. We had our, change per unit size. And it was gradient dot t. And let me just point out, gradient dot orientation is another way to say that. So something dot orientation, and then we wanted to know what is the something by itself. And notice that's the situation we're in here. Something dot orientation. Now the orientation's a normal vector. And so again, we want to know what is that something itself. So let's remind ourselves what we did in this case. What we did is we argued as follows. We said this thing here, gradient, we're going to call it an oriented density. The quantity in question is change. So I'm going to call this oriented change density. And why would we call this an oriented density? Well, because the magnitude tells us, in some sense, how much change is happening on this thing. Keep in mind the magnitude of the gradient tells you how steep the graph is. Right? How steep the graph is, another way to say that is how much does the value change as you move in the uphill direction. So in some absolute sense, this tells you how much the function is changing. And then the direction of the gradient tells you in what direction is that change maximally happening. Right? So I think this term is actually pretty reasonable, oriented, because it's telling us the direction that change is happening. And change density because it's literally telling us how much change per unit size as you move in that direction. Okay, so that's all familiar, I hope. That ring bells. Does that make sense to everybody? Any questions? Feel free. Okay, so with that in mind, note what I have here. It's laid out on the page very analogously, right? Same layout, right? So I'm trying to make the analogy as strong as possible. And again, we have this previously noted circulation density. Now we want to know how to make sense out of curl itself. I'm claiming that we should call it oriented density again, this time circulation as our quantity, so I'm going to call this oriented circulation density. Is that cool? I mean, it's the same pattern, right? I'm following along with the same pattern we did up here. And I claim we get the same interpretation of the gradient. Same interpretation here. Let me get my colors straight. And you know what? I didn't. Let me do like that. There we go. Let's see here. Okay, so the magnitude of the curl, I claim, tells us how much rotation is there in the fluid. So if you have a rotation in the fluid, the rotation might be something like this. The fluid is rotating around. Like imagine like a tornado, right? Of course, in a tornado, maybe it'd be more like this. The fluid is kind of rotating around, but it could be around any axis, whatever. Whatever that rotation is, there's either more of it, or maybe there's less. Maybe there's just a gentle, slight rotation, right? The magnitude of the curl tells you in some sense how much rotation is happening. In the same way that the magnitude of the gradient tells you how much change is happening. It tells you how steep is the graph. And how much change per unit distance as you're moving uphill. This tells you how much circulation per unit area. Around little boundary rotations. And then the direction of the vector tells us around what axis. So in the same way that the direction of the gradient tells you which direction on the map is uphill, likewise, the direction of the curl tells you if you have a rotation of your fluid, it tells you around what axis is that rotation happening. And so, for example, you can distinguish between a tornado-like rotation like this, right? So this is going around a vertical axis. Well, the curl will point in that vertical direction. Or if you have a rotation like that around that axis, well, then the curl will point in that direction. Okay, so I think the analogy is really very strong. I love these kinds of analogies. The point to this is I think y'all probably already have a good instinct for how the gradient works. Right? You're already pretty strong with the gradient. Well, that goes way back to chapter 2. You've had a lot of time to kind of digest that stuff. And so use this comparison, right, as you're trying to understand the curl. What does the magnitude mean? What does the direction mean? Well, it's very analogous to the answers to those same questions for gradient. What does the magnitude mean? What does the direction mean? Totally analogous. Okay. One last little comment. This is just a terminology thing. I really like this term oriented circulation density. If only because of how strongly analogous it is to this term, oriented change density. Oriented tells us that we're understanding it as a vector, that the direction's going to mean something. Circulation tells us what is the accumulating quantity that we're even talking about, just like up here, change tells you the quantity we're talking about over there. The analogy, it just really helps with the analogy to use a term like this. Outside of Math219, this is not the common term. There are different terms that I've seen. The more common one that I've seen is vorticity. And I think that's also actually a pretty natural choice. Have y'all heard the term vortex? Vortex is a real, cool sounding word. But a vortex just is a reference to something rotating, right? Like a fluid rotating around some sort of an axis. Like a tornado is a vortex. Right? So curl, understood as vorticity, what that means is curl is telling you the nature of the vortex. It's telling you how strong of a tornado is this, and around what axis is the tornado happening. So it's really kind of a perfect term. Vorticity really fits in that sense. So anyway, be prepared to hear the term vorticity. And when you do, oh yeah, it's just curl. Okay. All right, now a picture of what we just talked about. Curl. When you have a fluid flowing around, something like that. So curl points like that. In particular, the direction tells you what is the axis that to whatever extent there's a rotation in the fluid, what is the axis that rotation is going around. And by its magnitude, it tells you, in some sense, how much rotation there is, whether this is a really strong, category 5 type rotation, or whether it's just a gentle, subtle rotation. This picture makes sense? Y'all willing to buy it? It's a very important picture to make sure that you retain. This is, great intuition for how to think about curl in some future context. Now, I want to try to persuade you that the dot product up here is a reasonable thing. So let's see here. Let me, what color am I going to use? I'll use orange. So this dot product right here. Why the dot product? Or said differently, given that it's a dot product, is the dot product consistent with the idea of the curl and the normal vector and the ds actually telling me how much circulation there actually is? So I'm going to try to persuade you of this by just showing you two different circumstances and showing how they both kind of track. They both make sense. This isn't going to prove anything. Think of this as just a couple of examples of the dot product formula making sense. So here we go. Here is a fluid flow. And let's ask the question, to what extent is that fluid flowing around this boundary, like so? And I appeal to your geometric sense of what's going there. I'm going to say there's actually quite a bit of circulation. So keep in mind what circulation is. Circulation says to what extent is the fluid flowing along that boundary. And, well, this fluid seems to be flowing exactly along that boundary pretty much. Right, the whole way around. So I'm going to say that there's a lot of circulation. The fluid is going along the boundary very nicely. What about the dot product? If I look at curl dot in, well, those two vectors are pointing very much in the same direction. Maybe not perfectly, but pretty close to the way I've got it drawn. And the dot product then would also be large, right? So the geometric appeal I'm going to make to y'all is that this is no coincidence, right? The fact that the fluid rotation lines up with the boundary is geometrically sort of linked to the fact that the axis the fluid is flowing around and the normal to the surface whose boundary you were going around are pointing in the same direction. So the two purple vectors pointing in the same direction is consistent with the two green round things lining up in the same directions as well. Everybody see how the geometry of that works? The purple lining up is consistent with the green lining up. And then analogously, let's consider the same rotating fluid. But this time, let's suppose we're interested in how it rotates along this boundary curve. And it doesn't really. This rotation is like so. and this rotation is just in a totally different direction. And you can, use your geometric imagination. To what extent, let's say this part of the fluid kind of along in here, to what extent is that flowing along the curve? It's not really at all. Right? So this is kind of a disconnect of the fluid and the boundary. And likewise, the lack of circulation is consistent with the lack of there being a good dot product between the curl and the orientation vector. So, and again, this is geometrically sort of natural. The fact that these rotations are in different planes, you might say, is consistent with these two vectors being in different directions. Does that seem like a reasonable? Again, this doesn't prove anything, but I think this is a plausible consistency check. Let's call it that. Okay, so let's see a physical interpretation. I think the fluids interpretation is the most natural one. And so let me remind you, we've already talked about this in 2 dimensions. And in 2 dimensions, if you have a fluid, we're going to represent the fluid by the velocity. And you could imagine I like to think of the water flowing on the surface of a river. We've used that example many times. And so here's such a fluid. And then you can talk about the curl of that fluid. The curl will tell you the extent to which some floating leaf or what have you will be rotating as it flows downstream. So this is an interpretation of curl, 2-dimensional curl that we took back in chapter 6. Hope that looks familiar to everybody. And for 3-dimensional curl, it's very, very analogous. Different because it's a different geometric circumstance, but it's totally analogous. So in particular, here we are in R3, and let's imagine we have some fluid being represented by a vector field, and I'm just going to say, suppose there is a rotational aspect to the fluid, and I could draw a bunch of there's a bunch of little vectors there, but use your imagination. Let's suppose that there's a rotation happening there. So the physical metaphor that I have to create can't be a leaf because, I guess maybe it could, but I think it's a hard thing because leaves don't float in the air; they fall in the air, right? So I like to imagine balloons 2 or 3 days after the birthday party, and their balance. They no longer, the helium no longer takes them up to the ceiling, and they just kind of have that perfect amount of helium where they just kind of float randomly in the room. So, okay, one of those balloons, and now here's the hard part. You have to try to factor out the fact that, tragically, balloons have these balloon knots at the bottom, right? And so the balloon knot always hangs down at the bottom because it's that little bit heavier. And so that messes everything up. So you have to imagine a balloon perfectly balanced where there is no knot at the bottom. So that's a tough one, right? Anyway, such a balloon. How would this balloon move? Well, it's going to move, however, in the same way that the leaf will flow downstream, this balloon will flow whichever direction the air currents go. But if there is a rotational element to that airflow, the curl, just like in 2 dimensions, the 3-dimensional curl will point in a direction telling you around what axis that balloon will rotate. And the longer the curl is, the faster the balloon will rotate. So very analogous. 2-dimensional curl, just kind of a 3-dimensional equivalent. Everybody willing to buy it? Okay, these next examples we are going to skip, and this is so you are not responsible for this stuff about magnetic fields and current flows. It is a fabulous example involving curl and Stokes' curl theorem, and we just don't have time. This is not really part of the course. This is a supplemental thing. I like to include a bunch of supplemental stuff when possible. I know y'all are mostly engineers, and when y'all take E&M classes, they will talk in great detail about how flow of charged particles creates a magnetic field, and the curl of the magnetic field will tell you the current flow field. And so anyway, you'll recognize at least, and I'll make a quick reference here, you'll recognize this sort of rectangular equation. It's a lot like the stuff we were doing on Friday, right, with gravitational fields and electric fields. This is very analogous. It's dimensionally different. Instead of three-dimensional integrals on the right, it's now two-dimensional integrals on the right. Instead of two-dimensional integrals on the left, it's kind of one-dimensional integrals. Keep in mind, circulation is a one-dimensional integral. So it's different in that dimensional sense, but strategically very, very similar. And I will point out that this equation and this equation, these two equations are both known as Maxwell's fourth equation. And they look like very different equations. They are related extremely strongly by Stokes' curl theorem. Right? Stokes' curl theorem is the way we connect these otherwise seemingly different statements, and that's why these two equations can go by the same name, because they're, once you know Stokes' curl theorem, they're basically the same statement. All right, I wish we had more time to do some more cool physics, but again, ultimately not really what this class is about, so it's, oh well. And likewise, this is kind of a follow-up example, and again, we're not going to have time for this either. Okay, so now I want to call back to Chapter 6. We had this thing called a local test, and in particular, here's what we wrote down. In R2, we talked about how being a gradient is simultaneous with being path independent, got our regularity issues aside, which is simultaneous with all circulations being zero. We talked about these all being simultaneous. We can make a quick, fairly direct argument that these two equations are equivalent. Again, you got to have regularity issues. And what was the way to connect them? The way we connected them was Green's theorem. So having done that, here's our local test. If you want to know if your vector field is path independent, you want to know if your vector field's a gradient, compute the curl, see if you get zero. That answers the question. Okay, so that's our local test. Then for the three-dimensional case, I had to kind of apologize and say we don't really have the proper tools yet, but in the same way that curl, two-dimensional curl, is the test in 2 dimensions, well, likewise, three-dimensional curl is the test in 3 dimensions, and I had to say, well, when we have the proper tools, we'll come back and revisit this. Here we are. We now have the proper tools to revisit. Let me see if I can get this all on the same page. Here we go. There we go. That's good enough. So, now in 3 dimensions, again, we know these 3 statements here are equivalent. Being a gradient, being path independent, having all circulations be zero. We know those are equivalent. Analogous argument for these statements here in blue. How could an integral always be zero no matter what surface you pick? That's crazy. Really? Always zero no matter what surface? Come on. How's that possible? Only if the integrand is itself zero. Okay, so we can make those analogous statements, and then here's where our new theorem fits in. In the place where Green's theorem was, it's now Stokes' theorem. And it fits in exactly the same, exactly the analogous place. Does that make sense to everybody? So it's morally equivalent argument. It's just, 3 dimensions instead of 2, and Stokes' theorem instead of Green's theorem. And you can very reasonably think of Stokes' theorem as being sort of a 3-dimensional version of Green's theorem. Very commonly described that way, by the way. You will very often hear this described as 3D Green's theorem. How we doing? This is just fulfilling that old promise from back in chapter 6. Okay. All right. Surface independence. This is a really cool one. Let me start by reminding you of path independence. And remember that in particular, path independence is a special property. Most vector fields are not path independent. Cannot emphasize that enough. Special property. Okay, now that said, what is this property? The property is that if you have one curve and you have another curve, and these two curves both start at the same point, these two curves both end at the same point. That is, these two curves have the same boundaries. Same start, same end. Okay. A path-independent vector field is a vector field for which the green integral will always equal to the blue integral. And this is an outrageous property. A path-independent vector field, you got to keep in mind, it's not just that it has to have the same value of the line integral for a given such pair of curves. It has to have the same line integral for all possible such pairs of curves, as long as those two curves have the same starting point and ending point. Right? This is a huge ask. It's to the point of being kind of implausible seeming. And again, I'll remind you, the very first time that someone told me about this property of path independence, I thought they were joking. I thought, well, there's no way. It's too many. There's countless different possible pairs of curves that have the same starting point and the same ending point. You mean I've got to make sure that all of those line integrals always pair up? They're always equal? That's insane. How could this possibly... That's too much to ask for a vector field. I was quite convinced this couldn't possibly be true. And of course, we've seen that it does work for many vector fields. So this is a thing. There do exist path-independent vector fields. Now let me remind you of the rephrase. The rephrase is that if you look at C1 and then go backwards along C2, note this minus sign indicating that we're going backwards along C2, thus making this new red curve, by the way, the boundary of that interior region. I need all these closed line integrals to be 0. So a path-independent vector field can instead be described by that alternative description. Okay, does that look familiar? This is again flashbacks to 6.3, I guess it was. So, a little bit of a while ago. All right. Let me draw this on our diagram, just as a reminder. Here's how I like to do it. Again, special vector fields. Not all vector fields. Cannot emphasize that enough. Path independence means that whenever you have two curves that have the same boundary points, we have to get the same value for the line integral. All right, so that's one way to write it. All right, now reminder: this diagram. What I like about this diagram is it's got a tremendous amount of patterns that are hidden inside of this diagram. So many patterns hold. Most patterns hold. Most anything that you can represent with a diagram of arrows and etc. at any point on this diagram, if you just translate over, it all still works. It's shocking how consistently these patterns hold. So with that said, here's an outrageous speculation. Let's slide over a notch. Let's speculate. Maybe, this is wild speculation, maybe there are some special vector fields that have this following outrageous feature, that whenever you take any two surfaces that have the same boundary curve, the fluxes through those two surfaces of that vector field will always give you the same value. This would be the equivalent, this would be the analogous property if, such a thing were possible. What an outrageous suggestion. How could this be possible? Any pair of surfaces? Any pair of surfaces that have the same boundary curve? Get out of town. How's that possible? Come on. You realize how many different pairs of surfaces there are that have the same boundary curve? You're telling me all of those pairs of surfaces have to give you the same flux? Come on. It seems like a lot to ask. Nevertheless, let's write that down. That's called surface independence. And one surface and another surface that have the same boundary curve. Okay, now I'm going to try to draw on here the shared boundary curve. Alright, we get that purple curve. By the way, you'll notice that I have oriented the green top surface upward. I have oriented the bottom blue surface also upward. And surface independence, the claim is that whenever you have, again, two surfaces with the same boundary curve, somehow we are supposed to imagine that the green flux and the blue flux would always be equal. That this special kind of vector field, this alleged, again, I don't know that this exists, but allegedly somehow there should be a vector field. Oh, I got my color wrong. I'm sorry. Somehow the green flux through this surface and the blue flux through this totally different surface should always be the same. Again, seems outrageous. And by the way, then quick observation, notice that if I imagine the surface that I get when I kind of glue them together, then we get a boundary of this solid region R. And another way to say surface independence then would be that this closed surface integral is always zero. So before we talk about whether this is possible, let's just observe. We're talking about really analogous properties. Right now, I've deliberately color-coded the same, so it leaps off the page as emphatically as possible. We're talking about morally the same concept applied in a different geometric circumstance. Okay. All right. So real quick, and we're not going to have time to finish this today, but let's see. Let me go back to path independence, and I'll remind you that the first thing we showed was that anytime you have a gradient of some function, any gradient is path independent. And I used the fundamental theorem of line integrals to show that any gradient is path independent. And you may recall it was the very first thing we did with path independence. We showed that all gradients are path independent, and the fundamental theorem was the way we did it. Then very shortly after, we showed that any path independent vector field, aka any gradient, would have curl equal to zero. And the way we did that was with Green's theorem at the time, and then as of a couple of minutes ago, Stokes' theorem to show the same result here in 3 dimensions. There we go. So Stokes' theorem showed that curl was equal to 0. Okay, so now what we've got then is this is what happened, right? We have special vector fields called path-independent vector fields. This theorem shows that every gradient has that property. This theorem shows that curl will equal to 0. So here's another outrageous speculation, completely unjustified. Irresponsibly speculative. Maybe all of this translates over. Now, again, that's not a proof. This doesn't prove anything. But maybe surface-independent vector fields, maybe I can create them as curls. Maybe all curls of something. Maybe curls are always surface-independent. And maybe Stokes' theorem will help me prove that. And maybe divergence of such vector fields will always be 0. And maybe Gauss's divergence theorem will be the way we will prove that. Wild speculation. And we're out of time and don't have the time to go through it. But roughly speaking, that's exactly the next thing we're going to do. Curls are surface independent. Stokes' theorem is going to be the thing that shows us that. Divergence is 0. That's our local test. And Gauss's theorem is the thing that's going to allow us to do that. So the diagram is unbelievably helpful. The diagram told us what to speculate and how we might prove it, and it was right. So something to keep in mind. I hope y'all are starting to become persuaded that there's a lot of good ideas inside of this diagram. We will pick up here next time. Y'all have a great Thanksgiving break. See you on next Monday.